everyone, and welcome. I'm so excited to talk to you today about the James Webb Space Telescope, the most powerful and largest space telescope ever launched. My name is Rachel from the Ontario Science Centre. My pronouns are she, her, and I'm joining you today from the ancestral lands and territories of the Anishinaabe Nation, which includes the Mississaugas of the Credit and Chippewa, the Haudenosaunee Confederacy, and the Huron-Wendat peoples, and is now home to many diverse First Nations, Inuit, and Métis peoples. The Ontario Science Centre is located in Toronto, which is governed by Treaty 13 with the Mississaugas of the Credit, and is covered by the Dish with One Spoon Wampum Belt Covenant. As a settler, I'm so grateful to be able to live and work on this land alongside the Indigenous peoples with whom we peaceably share this land and who've cared for it since time immemorial. Well, we're going to be talking a little bit today about the search for other Earth-like planets. That's not to say that our own Earth isn't special and unique and deserving of our respect and protection. Think about the ways that you connect with the land and help keep our planet safe. Let me know where you're joining from. Look forward to see where you're all joining from in the chat. Some of you may be joining from other locations today. We're always encouraged to find out more about the peoples, treaties, and land that we live on. There are several resources available. Ones that I found really helpful are the websites whos.land and native-land.ca. As I mentioned, today we're going to be talking about the James Webb Space Telescope. I'm going to do a little bit of an introduction talking about what telescopes are and how the JWST works, and then get into the science and lots of time for all your questions. Really looking forward to seeing them. So start typing those questions in the chat. While we're absolutely open to respectful dialogue and discussion, any offensive or inappropriate comments will be blocked to ensure a safe and inclusive experience for everyone. So I have a few images that I can show you right off the top because I want to give you a little bit of an intro, making sure we're all on the same page before taking that deep dive into the science of the James Webb Space Telescope. So I've got some images to show you here. Some of you may have looked through a telescope before. Raise your hands if you've looked through a telescope. Let me know if you're in the chat. Who here has looked through a telescope? Maybe you own a telescope. Maybe you've looked through one at the Ontario Science Centre, like what we see here. If you visited us, these might look a little bit familiar. And let's talk about these types of telescopes and what telescopes do. Telescopes collect light. You can think of them as big light collectors. And they help us see things that are very far away up close. Does anyone know the name of the tool that helps us see things that are very small up close? Works kind of in a similar way. So let me know in the chat if you know what that instrument or tool is called. So telescopes are collecting light, and they do it in one of two ways usually. They use lenses or glass, kind of like the glass in my eyeglasses here. Those are called refractors, that you've seen on the left. Or they use mirrors, like in my compact mirror here. Those are reflector telescopes. And so a reflector telescope is what the James Webb Space Telescope is. Now, I mentioned that telescopes collect light. I've got some different pictures of buckets here. We're going to think about telescopes as light buckets. If we consider some rain buckets, I want you to let me know which one is going to collect the most raindrops. We've got a little tiny red bucket there with a handle. We've got a purple one in the back. There's a large metal bucket. Which one do you think is going to collect the most rain? So let me know in the chat which rain bucket will collect the most water. Maybe you would use it to water your garden. The key thing is volume. So maybe think about the size of the buckets. There's one that's a paint can there. We're seeing a couple responses coming in now. And it looks like most people think that the large metal one in the back is the one that's going to collect the most rain. And yes, you're absolutely right. It is the one that's going to collect the most rain. So biggest bucket collects the most rainwater. Biggest telescope collects the most light. And so that's why we need a really big telescope to go up into space. And this is why the James Webb Space Telescope is so big. How big is it, Rachel? You might be wondering. It is so big that it is about the size of a tennis court and its mirror is 6.5 meters across. How big is that? You can think of that about the height of a 3-story building in total. So it is enormous. Now, it wouldn't be a space telescope if it wasn't in space. So if you get something that big, how does it get into space? How do you get it into the rocket? Well, you fold it. This is a very last picture of the James Webb Space Telescope, and you can see it's all folded up quite nicely and compactly. This is the last glimpse that humanity had of the James Webb Space Telescope after its launch on Christmas Day last year. It's flying away to its eventual orbit, 1.5 million kilometers away from the Earth. You can see there the curve of the beautiful blue Earth right there behind it as it moves away. And then the process of unfolding starts to begin. So let's see how that happened. So this is an animation of the James Webb Space Telescope and all the different steps that occurred. So this part that you're seeing right here, that little thing that's dropping that looks like a foot, that's the antenna. That's what sends the information back to Earth. There are over 50 different steps that had to occur in order for the James Webb Space Telescope to fully unfold. This is the most complicated engineering feat that's ever been attempted in space. 170 different tiny little latches that had to be detached so everything could work just as it was meant to. What you're seeing happening now, this diamond shape that is appearing, this is the sun shield. So the sun shield is 5 layers of a very delicate material. This is used to block out the sun and the earth and the moon, allowing the mirror and the instruments to remain very cold so they can operate at very cold temperatures. That's the secondary mirror coming down in front. And then you'll see kind of like a drop leaf dining table, like the sides of the mirror coming up on one side and coming up on the other. The mirror is in 18 different segments, and then piece by piece, bit by bit, they all came together into this fully unfolded and operational telescope. Pretty incredible. Now I have some props here that I can show you a little bit more detail about how this works. I have a paper model of the James Webb Space Telescope here. We're going to drop a link in the chat where you can download the instructions on how you can make your own paper model at home or in your class. And this is the antenna that I was talking about, just dropped at the bottom there. This is where all the motors are underneath. This is the large sun shield. All the instruments are behind the mirror here. This is the secondary mirror in front right here. So the light comes, hits the primary mirror, which is the gold mirror here, bounces off the secondary, and then goes right through the hole in the middle into the instruments in the back. And so that's how the James Webb Space Telescope works. And it looks quite different than maybe a telescope you might be familiar with. It doesn't have a tube, but that's okay because it's in space. The tube allows you to block out a lot of surrounding light, but because it's so far away from the Earth, it blocks out a lot of the light using that sun shield, and it can capture all the light that it needs using this beautiful 6.5 meter long mirror. But what kind of light is the James Webb Space Telescope looking at? There's different types of light. There's light we can see and there's light we can't see. And I want you to look around your room where you are. You might be in a classroom, in the room in your house, and I want you to start to point out different sources of light. Let me know what some sources of light you see in your room. Okay, and I'm going to hold up a couple different things, and I want you to tell me whether or not these are also sources of light. So I have flashlight, light bulb. I have a TV remote. I have, oh, this might look familiar to some of you, a thermometer. Yeah, so we've got a couple different things here. So do you think that these are maybe different sources of light as well? Let's consider that. I hope that you're spotting some light sources in your own classroom also. Some that I haven't mentioned that might be in your room, maybe a microwave, a radio. So these are all different things to consider. And I hope that you're having some fun spotting the different sources of light around you. I see some of you are saying the sun. Yes, the sun. Oh, if you're watching outside, the sun is an excellent, of course, natural source of light. All right, now I have an image I'm going to show you next of all the different types of light. And everything I showed you, those are all sources of light. Some of them are sources of light that we can see. Some of them are sources of light we can't see. So for the case of the TV remote and the thermometer, they use an infrared light, infrared signals. So they take infrared light, and that's what we're going to be talking about next. So you can see here in this picture, we have visible light, sort of like all the colors of the rainbow, and then there's the light that we can't see. Some of you might have had an X-ray before, so that's a form of light. Some of you may have heard of ultraviolet light, where we wear sunscreen to protect ourselves from the UV rays from the sun. There's microwaves and radio, which I mentioned, and infrared, which is what we're going to focus on next, because that is what the James Webb Space Telescope is mainly looking at. And you think of infrared light kind of like heat vision. For anyone who's watching who's maybe a bit older and has seen the Predator movies, you know, Predator hunts using infrared vision. There's also different animals that are blood-sucking animals like bed bugs and mosquitoes and vampire bats. So they see using infrared light as well. And these different pictures here on the left show you what something would look like in visible light. And then on the right, it shows you what it would look like in the infrared. And so you can see that together, it gives you a picture of with much more information. So all of these different types of light make up the electromagnetic spectrum. So that might be a new phrase for some of you, so we can say that together. Electromagnetic spectrum, and this is all the different types of light. If anybody's used night vision goggles as well, it's another example of seeing in the infrared. Now, why does the James Webb Space Telescope want to see in the infrared? So it can peer through the dust. You think like there's a dirty window, we want to be able to see through it. We want to wipe that dust away and see what's happening behind it. We want to see what's happening in the very early universe. We want to push away those clouds that newborn baby stars are forming in. You can see this is a glimpse at what we might be able to see with the James Webb Space Telescope. So this is a set of images taken by the Hubble Space Telescope. On the left, you have one in the visible light, and on the right, you have one in the infrared. These are called the pillars of creation, and these are where newborn stars are formed. And you can see in the image in the infrared on the right, so much more is revealed. We can see so many more stars. And so the James Webb Space Telescope is not only going to look at star formation and stellar life cycles, it is going to be able to look back to the early universe and study how galaxies change over time, see the very first stars and galaxies, and also look at other worlds around distant stars. Of these 4 different science goals, which ones are you most excited about? I think it's so hard to choose. I think I'm so excited about all of them. As you can see, I've got my pin here, my James Webb Space Telescope pin. I'm like so jazzed that this telescope is up and is going to like be exploring all of these different new things, and we're going to discover all these incredible things about the universe. I would just love to hear which you're most excited about. I'm going to focus a little bit more about 2 that Canada is very much involved in. So Canada was a big player in the James Webb Space Telescope. I think I saw somebody ask who owns the James Webb Space Telescope. It's not really owned by anyone right now, but there's a group of different people from around the world that have worked to build it. The European Space Agency has their logo on there in that image, as does NASA. And right alongside is the Canadian Space Agency. Canada is a major, major player in the James Webb Space Telescope. And that's because they've built instruments that are not only going to help point the telescope, that's the fine guidance sensor, the stellar navigator. So that's going to help it aim at where it's going to look. And then NIRISS. NIRISS, they like to call it the exoplanet specialist in the cosmic time machine. That's because it's going to look at exoplanets, these planets around distant stars that are going to be candidates for life potentially. And the cosmic time machine, because it's going to allow us to look all the way back to the early universe and see those very first stars. So there's Canadians from all across the country, University of Montreal, University of Alberta, in Victoria, in Toronto, all over the country that have guaranteed time because they helped to build the instruments on board this incredible telescope. Now, I mentioned exoplanets. How many planets do you think we've discovered so far around distant worlds? Now, let me know what you think in the chat. This is sort of an artist's view of a planet around a newly formed star. And this is going to be incredibly exciting. Canadians are looking at some of the first science research that's going to be done using the telescope is going to be looking at planets that are orbiting around distant stars and measuring their atmospheres, the gas that surrounds the planet, to detect different tracers of life. And so if we think about our own atmosphere, our atmosphere has different gases. It has oxygen that we need to breathe. It has the carbon dioxide that we expel. And we can look for different tracers around other worlds. So we would be looking for ozone. We would be looking for carbon dioxide. We would be looking for methane. So there's different gases that we can look for that James Webb will actually be able to detect. So it's possible that we might be able to measure whether or not there is life on some of these other worlds. And I'm seeing a few people saying 5 to 10 millions. Oh, somebody said 5,000. You're very, very close. Yes, we're just under 5,000 right now. Just over 4,900 exoplanets have been discovered so far. And what's so interesting to me is that on average, at least every single star has at least one planet around it. Based on what we've observed. Now, we've observed a very small part of the galaxy, but I think that those are really boggling numbers. Another thing that the Canadians are working on is they're looking at the formation of the very first stars and galaxies, and I saw some of you were super excited about that as well. The first stars formed differently than stars that would have formed, that we see forming today, and that's because at the very beginning of the universe, there was only hydrogen and a little bit of helium, but really only hydrogen. And so how stars form today, they tend to form in very cold clouds of gas and dust. The early universe was very hot and really only had hydrogen. So these stars would have been massive compared to the sun, hundreds of times the mass of our sun, and they would have exploded in a supernova explosion just very, very quickly. And then in doing so would have enriched our universe with all of these different gases. Everything that we're made of, the iron in our blood and the calcium in our bones and the different carbon and nitrogen and oxygen, the organic matter that makes us, and all the different other elements that make up all the things that we know of in our lives, these all would have been created in the very first stars. So by understanding how the very first stars formed, they can help us understand how we then came to be, the origins of ourselves. And I think that's just so incredible to think about ourselves as star stuff, that we are really made of these elements. The building blocks of life came from those first stars. And I think that is really one of the most exciting things that that I'm really looking forward to seeing from the James Webb Space Telescope. And I'm really, really proud of the work that Canadians are doing to look at those first stars, the first galaxies, and also the search for life on other worlds. So I'm going to take a look at some of your questions. I've been seeing lots of questions coming in. And so, oh, someone has asking, what is the first photo it took? So that's a great question. So the James Webb Space Telescope is just looking at its first light. Just a few days ago, it got first light. It's looking at a star in the constellation of Ursa Major, which some of you may know because inside Ursa Major is the asterism, the Big Dipper. So it's looking towards that part of the sky, and it's just using that star to focus all its mirrors. If you recall, I mentioned it had all these different mirrors, all these little 18 segments. So they all have to work together to make one picture. So it's using that star so that it can align the telescope and align the mirrors just right. So it's all in focus and it makes one lovely picture. And then we're not too sure what it's going to look at next. There's a couple different things that it might look at. It might compare to some images that Hubble took in the past, like deep field images of galaxies or some of those star forming regions like the pillars of creation, but we won't know until June. So that's going to be incredibly exciting to see when those images first come back. We have a question of how far can the telescope see? So that's a great question. Thank you for asking that. So you can think of distance when it comes to space in terms of time. And that's because it takes light a very long time to travel across our universe, across any extent of space. And so the James Webb Space Telescope will be able to look at objects that are so distant from us that it'll actually be able to see some of the first things that formed in our universe, about 200 million years after the Big Bang. And just another example of how light and time and distance work together. Next time you go outside and the sunlight hits your face, that light is already 8 minutes old because it took 8 minutes to reach the Earth from the sun. So we never see the sun as it is, always as it was 8 minutes ago. And that's why I think of astronomy kind of like time travel. Every time you look up into the night sky, you're looking into the past and you're getting to see all these objects from so long ago. And the further away, the more distant an object is, the further back you're looking in time. So James Webb Space Telescope is going to be able to look so after objects so far away. It's going to be able to look so far back in time. It's going to see the things that formed right after the Big Bang, to about 200 million years after the Big Bang. Somebody's asking, when was the telescope sent out into space? So this telescope has been under construction for about 25 years, if you can believe it. And that's all those different mechanisms, all those pieces that had to unfold. That all had to be tested very carefully on Earth. Fingers crossed that it all worked once it got into space. And then it was sent up on December 25th last year. And so we expect the first images to come back in June of this year. It's going to have a mission of about 5 years, but because its launch went so well, it actually has enough fuel to last over 10 years. So we could get a lot of incredible science out of the James Webb Space Telescope. And we're just scratching the surface. This is just the first you're hearing about it. And we're going to be hearing a lot more over the years to come. Something I want to ask all of you, how long do you think it took that whole telescope to unfold? If it was launched on December 25th on Christmas morning, how many days, weeks, months do you think it took to fully unfold? So I'll keep an eye on the chat to see how long you all think that is going to occur. How far is the James Webb Space Telescope from Earth right now? So right now it's 1.5 million kilometers away. I actually can show you where it is. Let me just I have an image that I can bring up to show you where precisely it is in its orbit around the sun. So the James Webb Space Telescope is not in low Earth orbit like the Hubble Space Telescope. And because of that, that carried with it a lot of risk. There was some issues with the Hubble Space Telescope when it first went up, and it actually had to go up and be serviced by astronauts. This is not the case for JWST. It is about 1.5 million kilometers from the Earth. And you can see there, it is beyond the Earth and the Moon. It is in an orbit around a point that's labeled there as L2. This is called Lagrange point 2. So this is actually a very stable place in the orbit around the sun. It's actually balancing the gravity of the Earth and the sun so that it will always stay in line with those two bodies. And that sun shield, it's so far away because that sun shield wants to block out the sun and the Earth, because any heat or light from the Earth or sun can affect its ability to detect very faint infrared light. So its sensitivity to that infrared light is why it needed to be sent so far away. So it had to become very, very cool in order to operate at those temperatures. And so, yeah, it's cooled down pretty much all the way now. On the cool side, it's about minus 233 degrees. It's so cold. I've seen a few people who are guessing how long it took to unfold. 1 to 2 months. 2 months. 4 days, 15 hours, 32 minutes, 2.5 seconds. I like that guess. I like the precision of that guess. 2 hours, 2 weeks. Yes, so 2 weeks, about 2 weeks, 15 days is how long it took to unfold. So the whole deployment finished around January 8th. Isn't that incredible that it happened so fast? All those different things had to occur. Thank you for sharing all of those great guesses. Oh my goodness, there's so many wonderful questions. Is there any limit to how many photos the telescope can take? That's a really interesting question. Thank you for asking that, Ashley. There's a limited amount of hours each year. And the scientists who worked on the telescope get guaranteed time at the beginning. So that's why it's super exciting that Canadians were involved at the beginning, because Canadians are going to get a dedicated number of hours. Outside of that, after the first year or so, then it's going to open up to more scientists who can then apply. They can propose different things they want to look at, and then those science proposals are approved, and then those scientists then get time to use the telescope. It's similar to how ground-based telescopes are used as well, in that astronomers put forward proposals. But what's super awesome is that this mission starts out with some guaranteed time. So it depends on what you want to look at and how much light you want to collect. The further away and fainter an object is, you'll need to collect more light to be able to see it. And so you'll need to have longer exposure times, for example. So you're just going to want to have more light on that object. So it really depends on what you're looking at, how many images you can take. But I anticipate some of the first things we're going to see are going to be some of those really flashy, very, very beautiful observations. Someone wanted to know how long it took to develop this technology. So the whole space telescope took over 25 years to develop and build and test. We're seeing also how much better is the James Webb Space Telescope than the Hubble Space Telescope. So it's sometimes called the successor to Hubble, but they're actually going to be working together. The Hubble Space Telescope is still operating, will still operate for probably another 10 years or so, maybe even longer. But the James Webb Space Telescope can see more in the infrared, and it's about 100 times more powerful than Hubble. Its mirror is about 3 times larger, and because it's so much further away, it can see those fainter, distant objects. have time for just one or two more questions. Oh, how many of the exoplanets could support life? Is there an estimate? That's a wonderful question. I think that's from Samara. That is an excellent question. So we don't quite know. So I mentioned there's about 5,000 that we've discovered so far. There's a lot of candidates that are still being looked at. And we have measured atmospheres of some of those planets, maybe about a dozen or so, not too many, but we haven't really found anything yet that's promising. And that's why using the space telescope is going to be a lot more helpful, because the range of what we need to measure is really blocked out by our own atmosphere. So that's why we have to go above the Earth's atmosphere, above the cloud tops, up into space, and then look at those planets from above. And most of the targets it's going to be looking at are what we call habitable planets or Earth-like planets. There are many candidates that we found that are habitable or Earth-like. I'm not too certain of what percentage of those 5,000 are, but most stars, as I already mentioned, have at least one planet around it. And we're seeing that many stars do have at least one planet in the habitable zone. And so that's what we're looking at, that habitable zone. What that means is it's not so close that water could be boiled off the surface, not so far away that water would freeze. It's in that Goldilocks region where it's just right, where water could be in liquid form. Now, there's lots of other conditions that make a planet habitable, but that's the one sort of main way you can think about it. I have time for one more question. I just have an update here. About 55 potential habitable exoplanets have been found. So yeah, so you can take that percent. And yes, I have time for just one more question. So thank you for that update so that I can provide that detail. Oh my goodness, so many good questions. I don't know where to end it. How many stars are there? I'm just going to go there. How many stars are there from Georgia and Miss Doucette's grade 2 class? So many questions. I'm so sorry I wasn't able to get to all of them, but we'll end off with this because it touches on all the different aspects of what James Webb is trying to do, is to look at the first stars, looking at how stars form, looking at how planets form around stars, and how stars evolve in their galaxies. Such a great question. Now, how many stars are there? There are over 200 billion stars in our own galaxy. That's called the Milky Way. So that's a 2 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. Okay, it's a big number. Our galaxy is medium-sized. There are galaxies that have over 1 trillion stars. There are galaxies that are smaller. But if you think about, there are over, on average, about hundreds of billions of stars in every galaxy. And there are, on average, about hundreds of billions of galaxies in the universe. And then, if on average, every single one of those stars has at least one planet, who thinks that it's possible? Probably pretty likely that there's going to be life out there. I've got my hand up because I think it's pretty likely. Those are very big numbers. And I'm not willing to rule it out right now. And I'm super excited for what the James Webb Space Telescope is going to tell us all about it. I saw so many of you are really excited about life on other worlds. And that's something that I'm super keen on as well. And somebody just asked, do you think it'll find life on our other planets? I totally think it's possible. Yeah, I think that's one of the main reasons that they built it, and one of the key research goals they have is they think it's very likely that they could use this instrument to either detect or rule out the presence of life on other planets. So thank you so much, everyone. This has been awesome. I really enjoyed all your wonderful questions. I'm so sorry I wasn't able to get to all of them, but they were excellent, and I love how engaged you all were. we'll hopefully be talking to you more about the James Webb Space Telescope over the coming months and years. So keep an eye out for that. As always, we love when you're able to join us here for our Ontario Science Centre live streams. Please continue to like, share, and subscribe to find out more about future events. If you want to learn a little bit more about the James Webb Space Telescope or take away some resources, we'll drop another link in the chat where you can find some FAQs that might have answered some of those questions I wasn't able to get to that are available in over 40 languages. So it's a really excellent resource. Hope to see maybe some of you make those paper models and then share them with us on our channels. Take care, everyone. Stay safe. And thank you so much. Have a great day. Bye.